Okay, so now we're going to address calculation of the reflectivity when the electron density profile is not a step function. So here, for example, you have an electron density profile that varies continuously. And instead of having just a kind of a sharp drop off as a step function. And the way we model these profiles is as a series of thin layers. Each one of these layers are shown here. And each one of these layers itself has a step function. So we still use the idea of a step function, but in the limit where we have very thin layers and many of them, then we can approximate quite accurately this smoothly varying electron density profile. So now rotate your perspective a little bit. Now this upper bulk phase is going to be here, upper. And so this is the incident electric field. This is the reflected electric field. This is the transmitted electric field in the bulk. So that's way down here. And now what I'm showing you here is the series of layers that I indicated to the left. And within each layer, there are electric fields, and each layer has a certain thickness. And so the task becomes, how can we model the electric field throughout all these layers in order to figure out what the reflection is? So since each layer has a step function variation from one layer to the next, we can use the Fresnel reflection and transmission coefficients that we had just derived a few moments ago. We assign an index of refraction and sub j to each of these layers. And sub j has the zeta and the beta parts, which I'll write the zeta part like this, which is basically what we had before, except I've taken an approximation for the small angles that are appropriate for our interests. And then again, the same sort of approximation for the wave vector. So at the interface, let's say here, this interface that I've indicated by this arrow right there, that's the interface between layer J and layer J minus 1. We use the Fresnel expressions for the reflection and transmission at that interface. And these are just exactly the expressions we had a few moments ago. I showed you the Fresnel reflection. I don't think I showed you this equation, though I actually derived this for you by words. This is from one of the boundary conditions that the T is 1 plus R. And so from that, you can also figure out the expression for the transmission coefficient in terms of these wave vector components. Now, within these internal layers, there was a lot of stuff going on. There were a lot of reflections and transmissions. But the way we characterize each layer, instead of trying to keep track of all the multiple reflections and transmissions, we characterize each layer as having a field that's going down. That's this field. So that's the net field that's going down, as well as this field. That's the net field that's going up. We indicate that by a plus for going up, and this one by a minus for going down. And so I can write the electric field in a layer J as just these two components, the one going down, the one going up. And they just have an amplitude, A sub j or B sub j, as well as the piece that indicates the Z component of the traveling electrodynamic wave, this e to the minus I, where it's minus because this is the wave that's going down. Remember, our Z coordinate here is pointed up. So we get a minus for going down, and we have a plus here for waves that are going up. And then what we need to do is we need to think about what happens to this wave as it goes through all these many layers. So let's imagine we start out at this position up here, just slightly inside the top of the layer J. So the electric field will do two things overall. It'll go from the top of that layer to the bottom of that layer. That's what's indicated by this red arrow. Then it'll be right at the bottom of the layer. And then to complete the process, it'll pass over to the other side of that interface. So we have these two parts. First, we have propagation through the layer. That's what I'm indicating here, this propagation. The propagation is just, we're just following the Z components because it's only the Z behavior that's important, just as it was in the earlier lecture. And so the only thing that happens when the field goes from the top to the bottom is that there's a phase shift of the Z component of the wave vector times the distance it travels, this K times dJ. And so this represents the wave, the phase shift of the wave that's going down. This represents the phase shift of the piece that's going up, the E plus. And so this matrix here represents what happens as the electric field propagates from the top of the J layer to the bottom of the J layer, but staying still within the J layer. I'm going to call that the propagation matrix J. The other thing that happens, as I mentioned, is we have to go basically from layer J to layer J plus 1, though really just staying right at this Z sub J minus 1 position. So what I end up relating is these fields. So this field is the field at that ZJ minus 1 position, but it's the field in the J minus 1 layer. And I want to relate that to this field, which is again at the same position, basically the interface just on the upper side of the interface. It's in the Jth layer, the EJ. And so I relate those two by what I call an interface matrix. And the way you derive that interface matrix, which is just relating the field basically differentially close to this ZJ minus 1 position, but in one case in the layer above, the other case in the layer below, the way you relate those two fields is to just use the boundary conditions that I talked about earlier. And if you use those boundary conditions, then you can derive this thing. This whole thing here is this I matrix, not just what's in the brackets, but also the prefactor. So I'm not going to do that derivation for you, but you can see we have these expressions, one matrix that allows us to follow the wave as it goes from the top down to the bottom, and the other which allows us to follow the wave as it goes just right across the interface. And then you can imagine just repeating that. You then go down to the next one, then you cross the interface. And so we can follow the wave as it goes through this series of layers just by basically repeating these matrices. The propagation matrix, which allows us to propagate there through a layer, the interface matrix, which allows us to go across the interface and on down, just as I showed you a moment ago. And so then we can relate these fields. These fields are this field, this E minus capital J plus 1, that's the incident field. And the E plus capital J plus 1, that's the reflected field. That's the one we want to find out. And so we can start out from those. We go through this series of interface. We have to go through this interface first, then we propagate, then we go through an interface, propagate, interface, propagate, and that gets us down to these fields, and these fields represent the fields in the lower bulk phase. And so these are just a whole bunch of matrices. You multiply them all together, you get another matrix, or what I'll call the matrix M. And that's basically the entire calculation. But then the question becomes, how do you get the reflected electric field out of this? You want to pull out one of these pieces. Specifically, you want to pull out this piece. And the way to do that is to realize that this E0 plus, that is the wave going up in the lower bulk phase, that would be a wave here, that doesn't exist. That's just 0, because the only thing that's in the lower bulk phase is the transmitted wave. And so this becomes 0. And that term, which is just the M21 here, times this, plus the M22 times that, which is what I wrote here, that's just equal to 0. As I said, the E plus here is the reflected wave, the E minus is the incident wave. We can just solve for the reflected wave, and that gives us the reflected coefficient, just the reflected E field divided by the incident E field. That's the reflectivity coefficient, and that's just the ratio of these two parts of this M matrix, and that gives us the expression for R. That's what's called the Parrot method.